Our solar system formed 4.6 billion years ago. As humans, it's really hard to understand how long ago that is, or to really conceptualize deep time. But to put it in perspective, if you started counting now from 1 to a billion, you'd still be counting in 95 years' time. So how do planetary scientists like me research events that happened so long ago? I'm Hannah Sanderson, and today I'm going to be telling you how I use magnetism to reveal the secrets of the early solar system and understand how Earth and its neighbours formed. Many things might spring to mind when you think of a magnetic field. An MRI machine, a compass, or even the holiday souvenirs decorating your fridge. But what does this have to do with understanding the early solar system? To understand, let's go back to the very beginning, to the birth of our sun. The sun formed from a giant molecular cloud, a dense region of gas and dust. Gas and dust was pulled into a ring, a structure we call the protoplanetary disk. Small bodies began to form there, some of which were up to 100 kilometers in diameter. As radioactive elements in these rocks decayed, the rocks were able to melt and separate into layers, forming a metallic core and a rocky mantle. And ta-da! Mini planets, or planetesimals. When these planetesimals collided together, they formed larger and larger objects until eventually we had the planets that we have in our solar system today. Remnants of these objects ended up in the asteroid belt, which is found between Mars and Jupiter. Parts of these asteroids can break off and come to Earth as meteorites, which is great news for me as a planetary scientist. It means we have an incredible way of studying the early solar system. Holding a meteorite is like holding one of the building blocks of our planet, and studying it in the laboratory gives us a way to look billions of years into the past. So what does this all have to do with magnetic fields? Well, amazingly, meteorites have a way of recording the magnetic field that existed on their parent body, almost like they've frozen a moment in time. And the magnetic field recorded in a meteorite can tell us a lot about the parent body that it came from. In order for a planetesimal to generate a magnetic field, there's a strict set of requirements. First, it must have a metallic core. Second, the core must be at least partially molten. And third, there must be vigorous flow within the core. When the molten material flows in the core, like a current through a wire, it generates a magnetic field around it. I write computer code to model the characteristics of planetesimals that enable them to generate a field at certain times. I then compare this to the fields we actually measure in meteorites. In this way, I can get a clearer picture of the parent body, like how big it was, the size of its core, and how fast it cooled. I have also examined the difference between bodies that form without water, that have large cores, compared to those that formed with water, that have smaller cores, and whether this leads to a difference in magnetic field generation. The answer is yes. Bodies that formed with water in them generate weaker fields for a shorter amount of time. This is because smaller cores generate weaker fields, and a small amount of water in this rocky layer means the rocky layer cools faster. This cools the core faster, which then leads it to solidify earlier, ending magnetic field generation. This can help us gain a greater understanding of things like the distribution of water in the early solar system, and how much water these objects retained as they heated up and separated into their layers, and also help us understand things like the size of their cores. So there you have it. Magnetism and meteorites can tell us an awful lot about the early solar system, and give us a glimpse into events that took place billions of years ago. To find out more about my research, head over to my website. The link's below.